Okay, so we are in section 5.3 and 5.4. We are still looking at torque and shear stress, and now we've added to that angle of twist and power. So let's just remember that our generic is T rho over J, where rho is some radial length. So our maximum occurs at that outside radius or the outside radius of the material. And then we have phi, which is our angle of twist, TL over JG. And then we also have power, and we have lots of possibilities with power, and we went over those in class. We have slides that kind of help you with the unit conversions. It's the only time in this class we'll have a lot of unit conversions. So we have a steel tube with an outer diameter of 2.5 inches. So our outer radius is 1.25 inches, which is C. It's used to transmit 9 horsepower. So our power is 9 horsepower when turning at 27 revolutions per minute. So we have this angular velocity of 27 revolutions per minute. Determine the inner diameter D of the tube so that the nearest eighth inch if the allowable shear stress is given. Okay, so the first thing we have to do is convert our power, because I know that my shear stress is a function of torque and that outer radius, and then J is going to have that inner radius in there. So I need to get a torque, and I can do that from power. So we have power equals torque times angular velocity, and we can rewrite this so that we have torque equals power over angular velocity. And this is where we have to watch our unit conversion. So I have 9 horsepower, and that's not a unit that I'm used to seeing in terms of pounds or inches, kips, whatever. And so I know that 1 horsepower using our conversion is the same thing as 550 pound-feet per second. Okay, now here on the bottom, I have 27 revolutions per minute. Well, I need to get this to seconds because I have seconds up here. So we have 1 minute is to 60 seconds. Okay, what is a revolution? So I think about it in terms of, again, that kind of unit circle or whatever. This is going to be 1 revolution. I also know that that is 360 degrees, and I also know that that is 2 pi. And so I just kind of keep that in the back of my head, or I actually draw it out if I need to. And so now I know 1 revolution is 2 pi, and we, work in radians. It's unitless or whatever. So we have 1 revolution that's going to go on the bottom. 1 revolution is equal to 2 pi. And now when we look at units, we're pound, feet, seconds go away, and then we have this radian. So our torque, if we multiply all of this out, is 9 enter 550 times, and then I have 27 divided by 60 times 2 times pi, and then divided by. So we have 1750.7, and these are in units of pound feet. Well, I need to be in kips and inches. So how do we get there? I know if I'm getting kips on the top, that is the same thing as 1,000 pounds. So it's just ratios. I need to get rid of feet. I need inches on the top. There are 12 inches in a foot. So I get rid of foot, pounds, and I'm back in kip inches. So divide by 1,000, multiply by 12, and I get 21 kip inches. So now we have our torque, so we can work on our shear stress. Our shear stress is T rho over J, where J is a function of the inner and outer radius. So I have my shear stress equals TC over J, which is TC pi over 2, and then I'm going to have C to the 4th minus inner radius inner to the 4th. And if I can get the inner radius, then we can get that diameter. So let's just go ahead and kind of rewrite this equation. And when I do that, I'm going to get that, we're going to rewrite C to the 4th minus radius inner to the 4th, that's what I don't know, equals TC over pi over 2 times that allowable shear stress. So honestly, then we could have c to the fourth minus this equals r to the fourth. So however you want to set it up. So I'm going to set it up where I have r inner, that's my inner radius to the fourth, equals t c pi over 2 shear stress, that's a negative, minus c to the fourth. So my torque was 21 kip inches. C is that outer radius, so 1.25 inches divided by pi over 2, 10 KSI, that's kip per square inch, minus 1.25 inches to the fourth. So let's look at this. This is kip per square inch, so that's going to go on top. So, and then the kips go away. So this is inches to the fourth minus inches to the fourth. That makes sense. So 21, 1.25 times pi as a number 2 divided by 10 times divided by. So I get 1.67 minus 1.25 enter to the fourth minus 2.44. And when I subtract those, I get a negative number. So I have negative radius enter to the fourth equals negative 0.7696 inches to the fourth. So my inner radius equals 2 times 1.54. And that is not the correct answer. So where did I go wrong in all of this? 21 enter, 1.25 times pi as a number, 2 divided by 10 times divided by 1.67, and then 1.25 enter to the fourth, 2.44, okay, minus, change signs, and then I need to go, I think I took it to the fourth, and I need to go the fourth root. There we go. That makes more sense, because that would have been, that radius of a 1.54 is bigger than the radius of the outer. So that's where I was like, it can't be 1.54. That's bigger than our outer radius. And it's because I didn't take the fourth root of this. I took it to the fourth. So we have 0.9368 inches, which means that our inner diameter 2 times is 1.874. And it said to the nearest 1/8 inch. So I'm going to look at this, and well, that's bigger than 6/8, which is 0.75. So let's see what 7/8 is, because I need to know where am I rounding to. 7 enter, 8 divided by. This is 0.875. So this is fitting right here in the middle. Okay, so now we have to think about, what are we doing? Do we round up, which is what we've done oftentimes with things, or do we round down, which is also what we've done? If I round to a bigger diameter, then I am actually creating a smaller thickness, and I'm decreasing the area that I need. So I don't want to round up and decrease that cross-sectional area. So I'm going to round down to 0.75 so that I can have a smaller diameter, which is increasing that thickness so that it's more thickness than the absolute minimum required. So I'm going to use a diameter inner of 1.75 inches.